Okay, so this is Chapter 4 now. We're going to be starting a discussion on trigonometric identities. So basically what a trigonometric identity is, you relate an expression involving trigonometric functions in terms of an alternative expression. And so we're going to be manipulating the definitions of the trig functions to construct different functions, different types of functions as the answer to a number of inquiries. Okay, so in the first category of trigonometric identities, we have what are called reciprocal relations of the trigonometric function. So we'll call this reciprocal relations. Okay, and as you might suspect, this would involve constructing rational functions. Reciprocal identities, we'll call these. All right, so for instance, we know that the cosecant of a function, or the cosecant function, that is equal to the 1 over the sine of x. Okay, so that's 1. We know that the secant function is 1 over the cosine of x. Okay. And these should be memorized. And let's see, then we have the cotangent of x is equal to the 1 over tangent of x. And then the tangent of x of course, its definition is the sine of x over the cosine of x. Okay, and then the cotangent of x, its definition is the cosine of x over the sine of x. All right, so all of these should be memorized. These are definitions. All right, okay, so we have those. All right, then we have, as we discussed in Chapter 2, we have the Pythagorean identities. Okay. Okay, and so these are relations such as sine squared x plus cosine squared x is equal to 1. Or if it's not the, well, we'll leave it at that. I was thinking if it's not the unit circle, we'll have something different, but we'll talk about that later. All right, and then, of course, we disclosed in Chapter 2 that if we divide both sides of this equation by the cosine squared x, we'll get tangent squared x plus 1 is equal to secant squared x. Okay, and then if we divide both sides of this equation by sine squared x, we'll have 1 plus cotangent squared x is equal to cosecant squared x. Okay, so these are the Pythagorean identities. Then we have even-odd identities. And for instance, we know that the sine of negative x is equal to minus sine of x. And we showed that when we graphed the sine function last class, or in Chapter 2, the odd property of the sine function. And, okay, and then we have, we know that the cosine of negative x, well, the cosine function is an even function. Okay, and we saw that with the graph as well as the function table. So I should say these are even-odd identities. Sorry, I forgot to label it. Even-odd identities. Okay, and then there's one more, and that is the tangent. Okay, so the tangent function is an odd function. So the tangent of minus x is equal to the minus of tangent of x. And the cotangent function is an odd function as well. And the secant function is even, and the cosecant function is odd. Okay. Then we have what are called cofunction identities. Okay, so this may be something new, but we kind of explored it last class. We just didn't call it cofunction identities. And we can review that again graphically. Okay, so before I write these down, I'll demonstrate them graphically what they are. So for instance, an example cofunction identity would be, say, like the sine of pi halves minus x. So what would its graph look like? Okay, so this would be a cofunction. So cofunction means that this sine function the sine function at pi halves minus x must be related to some other trigonometric function. So let's see what that would be. So what I'm going to do is I'm going to start off by, say, graphing y equals sine x. Okay, so y is equal to sine x. And let me set the window properties. Okay, so that's shown in red. And then how about we graph y equals cosine x? Okay, and so that's shown in blue. Now, somebody mentioned last class that should the sine of negative x equal to cosine x? Well, let's see what the sine of negative x looks like. Oops. I guess we have to go to the next one. Okay, so the sine of negative x, y is equal to sine of minus x. Okay, that will be shown in green. So as you can see from the graph, the green curve is not the same as the blue curve. Okay, so this would be the sine of negative x, shown in green. Now, what would be the sine of pi halves minus x now? What would that match up to? So let's graph that. So the sine, y is equal to the sine of pi over 2 minus x. Okay, that's the purple curve. And you can see that the purple curve and the blue curves match up. Okay? All right, just from a graphical experience. So purple and blue are aligned. So that means the takeaway is that the sine of pi halves minus x is actually the cosine function. Hence, sine pi halves minus x cofunction is cosine x. So we'll say that is equal to cosine x. All right? And we can do another experiment. Say we want to calculate the cosine of pi halves minus x. All right? So let's get rid of. So yeah, let's get rid of this one. Okay, and so now the blue curve is for cosine function. So how about if we have, now we know the cosine function is an even function, so the cosine of minus x is just the cosine of x. So how about if we calculate our graph, rather, the sine of pi halves, I'm sorry, the cosine of pi halves minus x. Okay, and when we look at that, we see that the blue curve lines up with the red curve. Okay, so we say that cosine pi halves minus x, the cofunction of that is the sine function. Okay, so there's a cofunction identity. Likewise, all right, so let's explore the cofunction of tangent pi halves minus x. So let's get rid of these and these. So here's the graph of the tangent function, shown in orange. Okay, and the graph of, now we know that the tan function is an odd function. Excuse me. So here would be the graph of negative of x, shown in black. Okay, so it's a reflection about the y-axis. Now, so then let's graph the y is equal to tangent of pi halves minus x. Okay, that's shown in red. Okay, so you can see we just take the black curve and we shift it to the left pi halves radians. Okay, you can see that. All right, so let's compare then the tangent of pi halves minus x with, say, cotangent of x. So y is equal to cotangent x, and this will be shown in blue. And you can see that the blue and the red curves line up. Okay, the blue and the red curves will line up. So therefore we say that the tangent of pi halves minus x, its cofunction is the cotangent x. And I won't show you, but the cofunction of the cotangent of pi halves minus x is, of course, tangent of x. So let's summarize then the cofunction identities on this slide. So we have sine of pi halves minus x is equal to cosine x. And we discovered that graphically. You can also discover this using a function table. The cosine of pi halves minus x is equal to sine x. And I believe WebAssign may ask you to verify this result using a function table as opposed to a graph. Okay? And so the tangent of pi halves minus x is equal to cotangent x. And of course, the cotangent of pi halves minus x is equal to the tangent of x. Okay, and then other functions that I didn't mention, the secant, of course, the cofunction of secant of pi halves minus x is equal to cosecant of x. And you can validate that graphically as well or through a function table. And then the cofunction of cosecant of pi halves minus x is equal to the secant of x. All right, so cofunction identities. Those are very important. All right, so oftentimes we'll be asked to simplify some trigonometric relationships. So for instance, suppose we want to simplify a function like this. So the tangent of x times the cosine of x times the cosecant of x. Okay, so when you simplify such functions, a suggestion would be, but it's doesn't always hold, would be to replace the functions with their identity or their definitions. So for instance, we know that the tangent of x is the sine of x over the cosine of x. Okay, and then times the cosine of x, and then we know the cosecant of x is 1 over the sine of x. So after simplifying, doing all the cancellations, the answer is 1. So consider something a little more advanced, such as this rational function. So cosine x divided by secant x plus tangent x. Okay, so we want to simplify that if possible. It may not be possible to simplify these. So by simplifying, we mean that there exists, when you get the final result, there are no more cancellations in the numerator and denominator. Okay, so in this case, we need to explore the fact that there may or may not be some cancellations. So secant x is 1 over cosine x, and then tan x is. Okay, and so we can add the terms in the denominator. So that would be 1 plus sine x over cosine x. Then we can do the division, so that would be cosine squared x over 1 plus sine x, okay? And then now we know that and we know cosine squared, we can use a Pythagorean identity and know that cosine squared x is simply 1 minus sine squared x. Okay, now the numerator becomes a difference of two squares. So we can factor the numerator. So I'm going to assume that you know how to factor a difference of two squares. Okay, and then we have a cancellation. So these terms cancel. And then we're left with 1 plus sine we're left with, oh, I'm sorry, that should be 1 minus sine x, sorry. I had 1 plus sine x listed twice. That should be 1 minus sine x, sorry. Make that correction. 1 minus sine x, okay? And so we're left with 1 minus sine x. Sorry, I didn't express the difference of two squares correctly, but this is correct now. 1 minus sine x times 1 plus sine x. Okay, so now we have the concept of being able to have to prove identities. So let's talk about proving identities. Next slide. Okay, so let me pull up the typewriter. Okay, so the procedure would be to start with one side of the equation, write it down, and then explore ways to transform this equation so that it will become the same as the other side. Become the same as the other side of the equation. Okay. So to do this, use known identities, use algebra, combine fractions, factor, and simplify. All right, so all of your algebra tools come into play now. And convert expressions into sines and cosines if necessary. All right, so, and of course, we need to work lots and lots of examples. So for instance, let me give you an example. Let's start off by saying we want to prove the following trigonometric identity. So suppose I give you this. The secant of x plus the cosecant of x divided by the tangent of x plus the cotangent of x. Okay, and I want to prove that that rational function is the same as sine x plus cosine x. So how do I do that? All right, so we can take the left-hand side and replace the reciprocal functions with their definitions in sine and cosine. So secant x is 1 over cosine x. Cosecant x is 1 over sine x. Tangent x is sine x over cosine x, and cotangent x is cosine x over sine x. Okay, and then we proceed to simplify that. So we'll add the terms in the numerator. So that would be sine x over cosine x sine x, because the common denominator excuse me, the common denominator in the numerator is cosine x sine x plus cosine x over cosine x sine x divided by, okay, and then the common denominator in the, for the two terms in the denominator would be cosine x sine x as well. So we'll have sine x, that would be sine x squared, right? Over cosine x sine x plus cosine squared x over sine x cosine x. Okay, so now coalescing the terms, we'll have the numerator becomes sine x plus cosine x divided by cosine x sine x, all of that divided by sine squared x plus cosine squared x all over cosine x sine x. So now remember, in a division, to do a division of two fractions, is what's going on here. Okay, you'd take the reciprocal of the denominator and multiply the numerator by the reciprocal of the denominator. So that's the rule for division. Okay, so if we do that, taking the reciprocal of the denominator, okay, we'll have this. Okay. All right, and so now we have a cancellation, right? That product cancels with that product, and then we know this is equal to 1 by the Pythagorean identity. So therefore, the result is established. Okay, so that's how you work these. Okay, all right, so let's do another one. How about we prove that let's see, I'm not sure if this will work, but we can try this one. Say cosine, we want to prove that the cosine x over the secant of x plus the sine x over cosecant x is equal to 1. Okay, so in this case, all you have to do is replace secant and cosecant with their definitions in cosine and sine. So we have cosine x divided by 1 over cosine x plus sine x over 1 over sine x, and so that's equal to cosine squared x plus sine squared x after you do the division, and that's equal to 1. Okay. All right, so let's prove this one. How about the sine of alpha minus the tangent of alpha times the cosine of alpha minus the cotangent of alpha. That's cotangent. Okay, so that product of those two factors should equal to cosine alpha minus 1. We want to prove this, okay? Sine alpha minus 1. Okay, so I guess we could start off by multiplying the two factors on the left-hand side. So if we do that, we use FOIL. So we'll have the first term, product of the first terms, sine alpha, cosine alpha. Outer terms, that would be minus sine alpha, cotangent alpha, plus the product of the inner terms, so that would be tangent alpha, cosine alpha. And then the product of the last terms, that would be plus tangent alpha, cotangent alpha. Okay, so this product is that, okay? And so we can simplify that. Well, we know this product right here goes to 1. And so we'll have sine alpha, cosine alpha. Okay, and the cotangent, of course, is cosine over sine, so this would just be the cosine alpha. And then this with tangent of alpha is, of course, sine alpha over cosine alpha, so that becomes minus sine alpha. Okay, and then we have plus 1. Okay, so now what can we do here? We can, so we can say, how about we factor out so we can say this would be, so now we need to factor this, right? So sine alpha times cosine alpha minus 1, so that those two terms factor, minus cosine alpha plus 1. Okay, and then we can factor further. We can factor out the cosine alpha minus 1, so this would be, well, before I do that, let me make it so it's apparent to you. So we'll have sine alpha times cosine alpha minus 1 plus, let's see, before we do that, why don't we make it a minus, so the factors will have the same sign. So this would be minus cosine alpha minus 1. Okay, you see how I took these two terms right here, and I factored out a negative here from these two terms, and I get this. Okay, so now we can factor out a cosine alpha minus 1. So this would equal to cosine alpha minus 1 times a sine alpha minus 1, which is what we want. Okay, so there's the proof for that. Okay. All right, so let's do another one. How about we want to prove this identity? The sine of x over 1 minus cosine x minus the cotangent of x is equal to the cosecant of x. Okay, so now one thing we can do is we can say, okay, sine x over 1 minus cosine x is we can bring the cotangent over to the right-hand side. Now, you don't have to do this, but the reason why I'm doing it is because I want to try and avoid having to subtract relatively too complicated rational functions. See, the denominator of this rational function is 1 minus cosine x. Well, that would involve having to find a common denominator of a lot of terms. But if I move cotangent x to the right-hand side, then finding a common denominator for the two rational functions is easier. Okay? And so all I need to do now is just simplify this and not worry about the left-hand side. Okay? So cosecant of x, of course, is 1 over sine x. And the cotangent of x is cosine x over sine x. Okay. And so now I have a common denominator. Oh wait, let's see. Cosecant is 1 over sine. Yeah. And so let's see here. I'm left with 1 plus cosine x over sine x. So it remains to show that does sine x over 1 minus cosine x, does that equal to 1 plus cosine x over sine x? Okay, so we need to demonstrate that now. Okay, so what if I were to say multiply the right-hand side by the conjugate of the numerator, which would be 1 minus cosine x, upstairs and downstairs by the conjugate. Okay, and so the right-hand side would become, well, we have essentially converts to a difference of 2 squares. So that would be 1 minus cosine squared x divided by sine x times 1 minus cosine x. Okay, and of course, let me fix that. It's not the exponent, right? Okay, that would be 1 minus cosine squared x. Okay, and of course, 1 minus cosine squared x, we know from the Pythagorean identities, is sine squared x. Okay, and then, so one of the signs cancels. And we're left with this. Okay, so we have proven that identity. Okay, so that's it for section 4.1. So proceed with your WebAssign questions for this assignment, for this section that is. Okay, so on to section 4.2. All right, so that's it for this section. Okay, so in section 4.2, or chapter 4, section 2, we're going to talk about addition and subtraction formula. And so what we mean by this is we want expressions for these things like cosine of the sum of two numbers. Okay, can we express the cosine of a sum of two numbers in terms of, say, cosine and sines of s and t? All right, so we're going to show that the cosine of a sum of two numbers is equal to the cosine of s times the cosine of t minus the sine of s times the sine of t. Okay, we will show this, and then we're going to show the cosine of a difference of two numbers will equal to the cosine of s times the cosine of t plus, that's a t right there, plus the sine of s times the sine of t. So the proof is rather lengthy, so you're not responsible for knowing the details of the proof. You are ultimately responsible for knowing these two formulae. Okay, and so perhaps if you want to memorize them, that might not be a bad idea. But even though the proof is rather lengthy, it's mostly algebraic and usage of simplifying trigonometric identities. So what we'll do, so prepare yourself, it's rather lengthy, so I'll start off with an illustration. Let me prepare it for you. Okay, so let's see here. Okay, and so note carefully this illustration. We have this arc T, which is kind of hard to see, but it's this black. So we'll call this distance arc length T right there. And note the labeling of the points. We're going to use this construction. And so note the distance is T. Okay, S plus T. Okay, it's the S plus T denotes the sum of the lengths, arc lengths S and T on this circle, and we'll take this to be the unit circle. And then note minus S, the distance minus S. Okay, so let me accentuate minus S. Minus S will be, say, that distance right there. Okay, so the coordinates of, say, point P0. All right, so we'll say point P0 has coordinates 1, 0. Okay, and point P1, okay, we know that the abscissa of point P1 would be the cosine of S plus T, and that's by definition. Okay, and the ordinate of point P1 would be the sine of S plus T. All right, so that's obvious. Now let's consider the point Q0. So Q0, oops, let me see. I'm sorry, Q0 is right there. So we'll call this S, negative S, sorry. That distance right there is negative S, okay? So Q0, Q sub naught, its coordinates would be, well, the abscissa would be the cosine of minus S, and its ordinate would be the sine of minus S. Okay? Which, of course, using the even property of the cosine function, that's just the cosine of S. And using the odd property of the sine function, the sine minus the sine of S. Okay? All right, so we have that result. And then the coordinates of Q1, you should readily see, would just be the cosine of T as well as the sine of T. The ordinate is sine of T. Okay, so I hope you understand how we extracted out the coordinates of these 4 points from the unit circle. And so now we can go ahead and make these relationships, identify some key relationships in the diagram. So clearly, arc length P0 to P1, okay, this is arc length. The arc length P0 to P1 is S plus T. And that happens to equal to the arc length of Q0, Q naught to Q1, which is S plus T, okay, assuming arc lengths are positive quantities. So S plus T. Okay, so you can see that. That readily follows from the diagram. So now, what do we do? Okay, so we can calculate the distance. So remember, what we had from Chapter 2, the chord subtending an arc. Chords subtending arcs of equal length have the same length. Okay, so these two chords that I've just accentuated in green, both of which have the same length. Okay, all right, so that's a result of geometry. So now all we have to do is use the distance formula. Okay, so use the distance formula. So P naught, so the distance from P1 to P naught, okay, so what is that distance? So P1 to P naught, the distance would equal to, remember the distance formula? The distance between P1, P naught in general, the distance between 2 points, in case you forgot the distance formula, that would be x, the abscissa of P minus the abscissa of P naught, the abscissa of P1 minus the abscissa of P naught squared, plus the ordinate of P1 minus the ordinate of P naught squared, okay? Now, these coordinates are written in terms of the trigonometric function, so, all right, so we know that the abscissa of P1 is what? Cosine of s plus t. So that we'll write cosine of s plus t. Oops, not this one, okay? And we know the abscissa of P naught is just 1, okay? And so now for the ordinate of P1 is sine s plus t. Okay, and the ordinate of P naught is 0. Okay, so that distance is P1 to P naught, and that has to equal to the distance from Q naught to Q1. So the distance Q1 to Q naught is equal to, okay, so the abscissa of Q1 is cosine t. Oops. And the abscissa of Q naught is cosine s. Okay. And then the ordinate of Q1 is cosine t. I'm sorry. The ordinate of Q1 is sine of t. I beg your pardon. Sine of t. And the ordinate of Q naught is what? Minus sine of s. So the minus minus translates to a plus. Okay, and we square that. Okay, so we have that. So now, these two distances must be the same. All right, so let's just focus on these two distances. Now, we can obviously, of course, get rid of the radicals by squaring both sides. Okay, so if we do that, we'll have, so we'll square both sides, and then we'll complete the squares of the binomial terms. Okay, so we'll have cosine squared of s plus t minus 2 times the cosine of s plus t plus 1. Okay, so these three terms result in the squaring of that. Okay, and then we'll have plus the sine squared of s plus t. Okay, all right, and so that would equal to now the right-hand side, which I'm going to square these two terms. So that would be the cosine squared of t minus 2 times the cosine of t cosine of s. Okay, plus the cosine squared of s. Okay, now I'll square these two terms. So that would be plus the sine squared t plus 2 times the sine of t times the sine of s plus the sine squared of s. Okay, so now I think we can simplify terms now. So now just focus on this equation. All right, so cosine squared plus sine squared of a quantity is, of course, 1. So then we get, so simplifying, we'll have 1. So these two terms right here evaluate to 1. So 1 plus 1 is 2. So we'll have the left-hand side becomes 2 minus 2 cosine s plus t is equal to, now these terms go to 1 and these terms go to 1. So that would be 2 minus 2 cosine t cosine s plus 2 sine t sine s. Okay, and we can divide both sides of this equation now by -2. Well, okay, so before we do that, we can see that these two will cancel because they're the same on both sides of the equation. And then we'll divide both sides by -2, and when we do that, we'll have cosine of s plus t is equal to, now divide both sides by -2, cosine of t, cosine of s, minus sine of t, sine of s, okay, which is what we want. So we have a relationship then. All right. So let's see what else we can do. Okay, so that would be the cotangent, well, the cosine identity, the cosine of a sum. Now, so let's see here. Let me check. Are the other ones? Let's see, this is section 4.2. So that really wasn't so bad there, the proof of the cosine of a sum. Let's see what else the book has to say. Okay, so now, how about the cosine of a difference? Okay, I believe that maybe worked in your book as well. So we're interested now next in saying the cosine of a difference of two numbers. So cosine of, say, s minus t, what would that be? Okay. So that would equal to cosine of s plus a minus t. Okay, and so we can convert the subtraction into an addition and then just replace t with minus t. So that would equal to cosine of minus t times the cosine of s minus the sine of minus t times the sine of s. Okay, and we can simplify. So we know the cosine of minus t because cosine's an even function. Cosine of minus t is just cosine of t. And we know the sine function is an odd function, so the sine of minus t is the minus sine of t. So that becomes the sine of t times the sine of s. Okay, so we have that. All right. Now, how about the sine of s plus t? So let's see. Perhaps we can make use of this formula, the red formula, to prove the sine of s plus t. Let's give that a go. So the sine of s plus t. Now, we know from the cofunction identities, see, we had a cofunction identity, right? We know that the sine of a number, well, we know that cosine of pi halves minus s plus t is equal to the sine of s plus t. Okay, so that was from lecture 4.1. This is the cofunction identity. So here's the utility of the cofunction identities. So we don't have to make some complicated geometric construction. All right, so in doing so, so all we have to do is just calculate this. All right, so using this formula right here. So this would be the cosine of pi halves minus s plus t. Perhaps we can say the cosine of pi halves minus s. Okay, that would be one term, and then minus t. Okay, and so we'll use the cosine of the difference angles to simplify this. So this would be the same as saying cosine of pi halves minus s plus minus t, like so. Okay, so we can group like that, and then we'll just do the same thing. So this would be so by the cosine of a sum of numbers, this would equal to the cosine of what? Minus t times the cosine of pi halves minus s, okay, minus the sine of minus t times the sine of what? Pi halves minus s. Okay, and so cosine of minus t is cosine of t. Cosine of pi halves minus s would be the sine of s. Sine of minus t is just the minus sine of t, so we can do this. And then the sine of pi halves minus s is, of course, the cosinus by the cofunction identity. So we have, the conclusion is that the sine of s plus t is equal to the cosine, the sine of s. I'll write it this way. I'll reassociate the sine of s times the cosine of t plus the cosine of s times the sine of t. Okay, so now for sine of s minus t, I think you guys have enough tools now to be able to generate what the sine of s minus t is. So you'll proceed just like we did here. Okay, so I'm going to leave that to you as an exercise not to be turned in. What else? What other identities can we work with? Okay, and then of course, I guess we can work on proving the tangent of a sum of two numbers. I'll prove the tangent of a sum of two numbers, and then I'll leave it to you to prove the tangent of the difference of two numbers. So we want to prove the tangent of s plus t is equal to the tangent of S plus the tangent of T divided by 1 minus the tangent of S times the tangent of T. Okay, so replace, of course, you can replace tangent with its definition. So tangent of S plus T is sine of S plus T divided by cosine of S plus T. Okay, and now just use the previous formulae. So substitute, so we'll have sine S cosine T plus sine T cosine S divided by cosine S cosine T minus sine S sine T. Okay, so we have that result. Now, so let's see here. We want tan S in the numerator, so we can divide upstairs and downstairs by cosine S. So, okay, so now it just becomes simplifying a trig identity, right? Do this. All right, so that would equal to the tangent of S times the cotangent of T, not cotangent, cosine, sorry. Cosine of T plus sine of T divided by cosine of T minus tangent of T sine of T. Okay, and now we'll divide upstairs and downstairs by the cosine of T, and so that would be tan S plus tan T divided by 1 minus tan, let's see, I think that would be, that should be tangent of S right there. Sorry, that should be tangent of S times the sine of T. Okay, so now, so we're dividing upstairs and downstairs by the cosine of T, so now we'll have the tangent of S times the cosine of T. Okay, so I expect you to be able to prove that, the tangent of a difference of two numbers using a very similar technique. Anything else in this section? Oh yes, okay, so a couple of notes here. So now, okay, so we can work some examples now. Yeah, just checking to see what we've got going on here. All right, so some problems. So how about evaluate without using a calculator, say the cosine of 75 degrees. So without a calculator, okay, we know that the cosine of 75 degrees would be the cosine of 30 degrees plus 45 degrees. And we know, okay, and so then we can use the cosine of a sum, so this would be the cosine of 30 degrees times the cosine of 45 degrees minus the sine of 30 degrees times the sine of 45 degrees. Okay, and so we know the cosine of 30 degrees is square root of 3 over 2. The cosine of 45 degrees is 1 over the square root of 2. The sine of 30 degrees is a half. and the sine of 45 degrees is 1 over the square root of 2. So that would be 1 over the square root of 2 times the square root of 3 plus 1 over, not plus 1, minus 1, excuse me. Square root of 3 minus 1 over 2. Okay, so now WebAssign will ask you to do this problem, and you'll have to leave your solution in radical form. Okay, so don't try to use a calculator for these types of problems. You'll need to express it in radical form. All right, so how about the cosine of pi 12ths? Okay, so let's express this answer in radical form. Okay, well, turns out that pi 12ths, okay, so we need to express pi 12ths in terms of a sum or difference of familiar quadrantal angles. And so it turns out that pi 12ths is equal to pi 4ths minus pi 6. Okay, and we're familiar with the cosines of pi 4ths and pi 6. We don't know what cosine of pi 12ths is, but we have to reformulate pi 12ths in terms of things we know, the sum or difference of things we know what the cosines of. So this would be the cosine of pi 4ths minus pi 6. So that would be the cosine of pi 4ths times the cosine of pi 6 minus the sine of pi 4ths times the sine of pi 6. Okay, and so that would equal to 1 over the square root of 2 times 1/2 minus 1 over the square root of 2 times the square root of 3 over 2. Okay, and so factoring out 1 over the square root of 2 times, that would be 1 minus the square root of 3 over 2. Okay, all right, so cosine of pi 12ths. Okay, so how about we do it in reverse? So how about we find a value for the sine of 20 degrees times the cosine of 40 degrees plus the cosine of 20 degrees times the sine of 40 degrees. Okay, so you should recognize that that's just the sine of the sum of two angles. So this would be the sine of 20 degrees plus 40 degrees, which is equal to the sine of 60 degrees, which is equal to the sine of pi thirds, which you have memorized as being the square root of 3 over 2. Okay. All right. Prove, say, this identity, the cosine. What is this equal to? Okay, so we've done this graphically already, but we can use the fact that this is the cosine of a difference. We know to be cosine of pi halves times the cosine of u plus the sine of pi halves times the sine of u. Now we know the cosine of pi halves, that's just 0. So this is, and we know the sine of pi halves is 1. So that's just equal to the sine of u. Okay, all right. How about, don't use purple enough. Okay, how about 1 plus the tangent of x divided by 1 minus the tangent of x is equal to the tangent of pi 4ths plus x. Okay, so it would probably be easier if we use the right-hand side. So we know that the tangent of a sum is equal to the tangent of pi-4 plus the tangent of x divided by 1 minus the tangent of pi-4 times the tangent of x from the identity we proved previously. So we know the tangent of pi-4 is 1. Okay, so that's 1, and so that would be 1 plus tan x over 1 minus tan x. Okay, see how that works? Okay. So we also have the difference quotient of a function. So recall from Chapter 1 lecture notes. What the difference quotient of a function is. Okay, so we said that that was equal to f of x plus h minus f of x over h. So do this for all 6 trig functions. I won't do it. I'll leave it to you to do it. And if you have any questions about doing it, see me. Now this could be a WebAssign question. Okay, but it's, so do this, find the difference quotient for each of these functions. Okay, could be a test question, could be a WebAssign question, could be both. All right. Let's see. Oh, okay, then we have some other concepts. So let's consider this. Let me prepare a drawing for you. Stand by, I'm preparing a drawing. All right, so consider this drawing. Here we have a radial arm of length a squared of a squared plus b squared. We have an angle phi, initial side on the x-axis, and then the terminal side with the terminating point at coordinates AB. So you see this kind of a right triangle kind of arrangement here. And so what we want to calculate from this figure, using this figure, would be this quantity. What is a sine of x plus b cosine of x? We want to calculate this particular sum. Okay, so now we know that, let's see, a sine of x. Okay, so using the results of this figure, this is b right there. That's b. So the way we can do this is we know that the cosine of phi, of course, is adjacent over hypotenuse. From Chapter 3, we know that. And we know the sine of phi is equal to opposite over hypotenuse. Okay, so we have those relationships. Now, we also can transform the equation. We have this. So let me replace x with phi, because I'm going to be in terms of the diagram here. Oops, looks like a D, doesn't it? So we'll have So let's do this. Let me multiply the expression by a squared plus b squared, the square root of, and then I'll divide each term in the sum by that. So I'll have a over so if we do something like this, times the sine of phi plus b over a squared plus b squared times the cosine. Okay, so we have something like this. Okay, and so then what we'll do is we'll replace let's see, what do we replace? Okay, so we have that. Did I want to use, no, actually I didn't want to use phi, I wanted to use x. So let me change that. Let me change the argument to x. So let's change the argument to x. Let me make that x. So let's make this x. Okay, so we'll use x because okay. That's the cosine of x. Sorry. Okay, so this expression is, we can reformat it this way. Now, so we know that the coefficient on sine x on this term right here will be the cosine of phi. Okay, so we can make the substitutions. This would be the cosine of phi times the sine of x plus, and we know b over the square root of a squared plus b squared is just the sine of phi times the cosine of x. Okay, and so after simplifying, we have the term in brackets then becomes the sign of a sum, which would be the sine of x plus phi. Okay, so turns out that this sum, a sine x plus b cosine x, is equal to the square root of the amplitude, the square root of the squares, the sum of the squares of the amplitudes, which is your new amplitude, times the sine of x plus phi. Okay, and phi is your phase shift. Now what is phi? So phi depends on which quadrant you're in. Okay, so we know we can divide sine phi by cosine phi, and we'll see that if we do the division, the tangent of phi is equal to b over a. Okay, so a very important relationship. So we have this. If you're adding a sine x plus b cosine x, it's the square root of a squared plus b squared times the sine of x plus b, where phi is equal to the tangent, or tangent of phi is equal to b over a. Now remember, depending on where b and a are, the sign of the tangent of phi varies, right? So you have to be careful when you calculate phi if you're going to use the tangent function. So for instance, give you an example. You have to be careful which quadrant phi is going to be in. And that depends on the coefficients, of course. So for instance, we can do this one. So f of x is equal to 3 sine x plus 4 cosine x. All right, so express this in terms of the sine function. So in this case, our coefficient, let's say k, would equal to the square root of, say, 3 squared plus 4 squared, which I believe is equal to 5. Okay, and let's see, the sine of phi, well, we have the tangent of phi would equal to, well, perhaps we don't even need to do this, okay? The sine of phi would be, okay, so we probably have to draw a right triangle. In this case, a is the coefficient, so here's a. So a would be 3, and b would be the coefficient on cosine function. Okay, so we have this, and so, okay, so it's a quadrant 1 angle. So the tangent of phi would equal to the opposite side divided by the adjacent side. And then you can use your inverse tan key on your calculator to discover that phi is equal to the inverse tan of 4/3. And so that turns out to be 53.1 degrees approximately. Okay, and so now f of x then would equal to k times the sine of x plus phi. Okay, and so that would equal to 5 times the sine of x plus 53.1 degrees. Okay. All right. So one more problem we can do for section 4.2. How about we graph this function without a calculator? Minus sine 2x plus the square root of 3 cosine 2x. Okay, so we want to graph that. So take 2x to be u. So let 2x equal to u. And so f of, so our function, so we'll let g of u be a new function. That would equal to minus sine of u plus the square root of 3 times the cosine of u. Okay, so that'll be a temporary transform, and then we'll come back to f of x once we simplify g. So in this case, for g, our a equals to -1, our b is equal to the square root of 3. Okay, and so what would be the phase angle? Okay, so a is -1, and b is equal to the square root of 3. So our angle would be somewhere in quadrant 2. Okay, so this would be our angle. So we know that the tangent of phi would equal to -1 over the square root of 3, and that's in quadrant 2. So that would make for, well, we know that the sine of phi over the cosine of phi would have to equal to, say, 1/2 over negative square root of 3 over 2. Right? It would have to match up something like that because the cosine is negative in quadrant 2. So that means the sine of what is equal to 1/2? That would be 60 degrees, right? So the reference angle would be, this would be 60 degrees. Okay, and so that would have to be pi thirds reference angle. Okay, that's your reference angle. So in quadrant 2, then this would translate to 2 pi over 3. Okay, so that's our angle. Phi is equal to 2 pi over 3. Okay, and the way we know this is because we memorized it from the table. We convert negative 1 over the square root of 3 to, we know that sine and cosine values of reference principal angles or familiar angles, the sine and cosine of familiar angles, how we can arrange 1/2 divided by the square root of 3 over 2 to get 1 over the square root of 3. These are the familiar angles. And then we know by familiar angles that the sine of pi thirds is 1/2, the cosine of pi thirds is the square root of 3 over 2, neglecting the sides in terms of the reference angles. Okay, so phi is 2 pi over 3. So what is our amplitude? We call it k. So that would be the square root of 1 squared plus the square root of 3 squared. So that would be 2. Okay. So now our g of x then is, or excuse me, g of u would equal to 2 times the sine of u plus 2 pi over 3. So now we can get back to our f of x. So we know that if we if we replace u with 2x, we'll get back our f of x function. So replace u with 2x. Okay, and so we're almost there. So now this would equal to 2. Now to get the period, we have to factor out 2. And that would be x plus pi thirds. So our phase shift would be pi thirds to the left. Okay, so we have that result. All right, so now period is equal to 2 pi over 2, which is equal to pi. Amplitude is equal to 2. Phase shift is equal to pi thirds left. Okay, so that's sufficient to graph the function. All right, so we can start off by graphing a sine function with period 2. So now a sine function with period pi, that is. So what you do is kind of like what I talked about in lecture 2. We take the 4 intervals, okay, and so we take pi, which is the period, and we divide it into 4 subintervals, 4 equal length subintervals. Okay, so this would be pi halves. This would be 3 pi over 4. And this would be pi over 4. All right, and then and so we draw one complete period of the sine function on this interval. And so we know in one complete period, the sine function starts at 0, goes up to 1, but in this case our amplitude is 2, so it'll go up to 2. Okay, so one complete period. So the first quarter length of a complete period, the sine function goes from min to max. Then in the second quarter length interval, the sine function goes from max to 0. No, okay, so hang on. In the first quarter length interval, the sine function goes from 0 to max. In the second quarter length interval, the sine function goes from max to 0. In the third quarter length interval, the sine function goes from 0 to min. And in the fourth quarter length interval, the last quarter length interval, sine function goes from min to 0. Okay, so there's the sine function sketched without its phase shift. Okay, now we need to incorporate the phase shift. So all we need to do is shift the curve left to the pi thirds unit. So let's see, I don't want that. I want, let's see if I can do it. So we take this, and we shift it to the left pi thirds. So it's going to look something like that. Let's see, I need to take the curve. Let me see if I can take the curve. So I'm going to take this curve, and I'll basically shift it to the left, pi thirds. So pi thirds is greater than pi fourths, so it's got to go something like this. Let's see, that won't work. Okay, so perhaps if I took the red, so this is pi fourths, so what is pi fourths minus pi thirds? So pi fourths minus pi thirds is equal to what? 3/12 minus pi 12. Okay. And then what is pi halves minus pi thirds? That's equal to what? Pi 6. And then what is 3 pi over 4 minus pi thirds? So that would equal to what? 9/12 minus 4/12, pi 12. And then pi minus pi thirds is 2 pi over 3. Okay, so 2 pi over 3. Okay, so pi fourths goes to minus pi 12. Pi halves goes to minus pi 6. Okay, and then 3 pi over 4 goes to 5 pi over 12. Just get that right here. And then pi goes to 2 pi over 3, which is there. Okay, so therefore we'll go to 2, we'll go to 0. Let's see, 0 to 2 to negative 2 and back. Okay, so your graph, let's see, 1, wait, I forgot an interval. So pi fourths goes here, pi halves goes to the pi 6. Oh, yeah, so we gotta go to pi halves goes to pi 6. 3 pi over 4 goes to pi over 12. Okay, wait a minute. Pi halves goes to pi 6. Pi 6 is where? This is pi 6. So, okay, pi fourths, oh, it went to 1. Oh, okay, sorry. Pi thirds goes to 0, sorry. So, pi thirds goes to 0. So, so the curve will go something like this. This too. All right. Okay, so the red curve is the blue curve shifted pi thirds. So this would be negative pi thirds here. This would be negative pi 12ths here. This would be pi 6 there. And then 5 pi over 12 here. And then finally, this would be 2 pi over 3. Okay, so there's the red curve, shifting the blue curve. Okay, so we can graph this function now without the assistance of a calculator. How cool is that? Okay. All right. Okay, so anything else? Okay, so I believe with that we can close out section 4.2. All right, so section 4.2 concluded.